In this videotape, we're going to learn how to calculate the derivative using the definition of the derivative. Some people call this the long method. Now, many of you already know a short method for finding the derivative, and you may find this a bit of a pain. But the truth is, when you come to a new function that you haven't worked with before and you want to calculate its derivative, you really have no choice but to go to the definition of the derivative. Let's look over here at the definition of the derivative. Now, f prime of x is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, provided this limit exists. Many textbooks use this form of the definition of the derivative. Some textbooks use this form. They write f prime of x, the derivative of f of x, is the limit of f of x plus h minus f of x over h as h approaches 0, provided this limit exists. Now, these are really basically the same. The only difference is that the people who use this definition are using one single letter h to represent the same variable that they're using two symbols, delta and the x, to represent over here. Now, h and delta x basically mean the same thing. And I would prefer to use this second formula. I think it's easier. Because when you have to calculate things involving delta x, for example, let's say you want delta x times x. This is the same as, of course, x times delta x. Some people make a mistake. They think that the delta and the x are separate. They're not. They're glued together. This represents a single variable. You cannot write this as delta x squared. These x's cannot multiply each other. This is delta x, this is x, and they are separate. It's a little easier if you're using h instead of delta x, because if you want h times x, you're not going to make any mistakes. Similarly, x times h. So I think it's a distinct advantage to use one letter to represent a variable rather than these two symbols taken together to represent a variable. So we're going to be using this form of the definition, although you would get the same answer if you use the delta x form. Okay? So we'll be using this form. F prime of x is the limit of f of x plus h minus f of x over h as h approaches 0. Okay. Now, if we're going to be using this form of the definition of the derivative, let's say we have a problem. We want to calculate the derivative of polynomial f of x is x squared minus 4x plus 3. We have to understand how this function notation works. F of x is x squared minus 4x plus 3 tells us that f of anything is that something squared minus 4 times that something plus 3. Notice how I've gone through the definition of the function, and every time I see an x, I've replaced it by parentheses. This will enable me to substitute anything I want in for the x. For example, f of 1 would be 1 squared minus 4 times 1 plus 3. And f of 5 would be 5 squared minus 4 times 5 plus 3. This function has one role in life. Okay? If you want to evaluate at a certain number, you take that number, you square it, you subtract 4 times the number, and you add 3. F of anything is that something squared minus 4 times the something plus 3. Now let's look at the definition of the derivative. We're going to need f of x, but that's what you're given originally. We're going to need f of x plus h. Now, if you rewrite the function with parentheses replacing x, then you'll be able to substitute in x plus h. F of x plus h would be accordingly x plus h quantity squared minus 4 times x plus h in parentheses plus 3. F of anything is that something squared minus 4 times that something plus 3. So f of x plus h is x plus h squared minus 4 times x plus h plus 3. This is what we're going to need in order to get started in calculating the derivative of this particular function. Okay, let's go to the definition and actually work it out. Remember, the function under consideration is x squared minus 4x plus 3. F of anything is that something squared minus 4 times that something plus 3. And f of x plus h is x plus h squared minus 4 times x plus h plus 3. Let's substitute in these values in the formula. We have the limit as h approaches 0. We need f of x plus h, which is waiting for us over here. That's x plus h quantity squared minus 4 times x plus h plus 3. And we have to subtract off f of x, which was the function as it was originally given to us, namely x squared minus 4x plus 3. This divided by h, taking the limit as h approaches 0. Now, many limits can be evaluated by substitution. For example, if I asked you to tell me the limit of h squared plus 3 as h approaches 0, you could simply let h be 0, substitute for h 0, and you get 0 squared plus 3, and you would know that the limit is 3. This is a consequence of the fact that this function here is continuous at 0, and the limit can be found by substitution. Now, you can never get by that easy when you're calculating a derivative, because the form of the limit that we're going to be evaluating is a limit as h approaches 0 of something that has h in the denominator. Now, we can't simply substitute h equal to 0, because that would give us division by 0. In fact, as h approaches 0, this becomes f of x minus f of x. So not only is the denominator approaching 0, but so is the numerator. When the denominator and the numerator are both approaching 0, we have to, if we're going to evaluate this limit, try for some sort of algebraic maneuver. Our goal would be, if it's possible to factor an h out of the numerator, that h could cancel the h in the denominator that's causing all the trouble, and then maybe we'll get to a situation where we will be able to find our limit by substitution. But as it stands now, we simply cannot let h be 0 in this formula. Okay, so let's see what we can do. We have the limit as h approaches 0. Now, x plus h squared is x plus h times x plus h. Just reminding you, x plus h squared is x plus h times x plus h, which is multiplying binomials using FOIL. First, x squared, the outer, plus hx, the inner, plus hx, and the last, h squared. The first terms, the outside terms, the inside terms, and the last terms. The so-called FOIL method for multiplying binomials. So x plus h squared is going to be x squared plus 2hx plus h squared. X plus h squared, x squared plus 2hx plus h squared. So let's write that in here. X plus h quantity squared is x squared plus 2hx plus h squared. Now, minus 4 times x plus h in parentheses. The minus 4 must be distributed through the parentheses to give us minus 4x minus 4h. Okay, many people forget, and they get minus 4x plus h. Either they forget to distribute, or they forget the parentheses, so they don't realize that they have to distribute. But it's minus 4 times the x and minus 4 times the h, plus 3 minus, now x squared, minus 4x plus 3 all over h. This gives us the limit as h approaches 0 of. Now, you really did not have to have the brackets around f of x plus h. It's x squared plus 2hx plus h squared minus 4x minus 4h plus 3. But it's crucial to keep the brackets around f of x if f of x contains more than one term, because when you subtract f of x, it's really like distributing a minus 1 through this parentheses. In other words, the sign of each term here has to be changed. It's minus 1 times x squared, that's minus x squared. Minus 1 times minus 4x is plus 4x, and then minus 3. The minus has to be distributed through the parentheses, all over h. Now, let's see if we can simplify the numerator. We have a plus x squared and a minus x squared. They cancel out. We have a minus 4x and a plus 4x. They cancel out. And the plus 3 and the minus 3 cancel out. So when the smoke clears, we're left with the limit as h approaches 0 of 2hx plus h squared minus 4h all over h. Let's write that up on the top here. It's the limit as h approaches 0, 2hx plus h squared minus 4h all over h. Now, the nice thing is that at this stage, we can factor in h out of the numerator. The numerator is h times 2x plus h minus 4. Now we have over h, taking the limit as h approaches 0. Now, as h approaches 0, it's getting close to 0. It's not equal to 0. And because it's not equal to 0, we can cancel the h's. Canceling is really a type of division. What we're really doing is dividing numerator and denominator by h. Well, if h is not 0, but just close to 0, you can divide numerator and denominator by h, leaving us with the limit as h approaches 0 of 2x plus h minus 4. At this stage, the limit can be found by substitution. As h approaches 0, if this goes to 0, we will be left with simply 2x minus 4. This will be the derivative of f of x. F of x is x squared minus 4x plus 3, and we have just shown that f prime of x is 2x minus 4. Now, many of you have already studied the short method for finding the derivative, and you know how to go from here to here in your head. However, when it comes time to study the trig functions and you want to work out the derivative, for example, of the sine function, you will have no recourse except to go back to the definition of the derivative. So it is important that you understand that you are responsible for the definition of the derivative, even if you know a short method for calculating derivatives. Now, basically, if you can master 3 types of functions using this definition, you'll probably be all right. First of all, we have polynomials. Now, with polynomials, you get what we have over here. You have to expand usually something, subtracting off f of x. Usually f of x cancels out over here. And then whatever you're left in the numerator with has h as a factor. You factor out the h cancels with the h downstairs, and you find your limit by substitution. Polynomials generally work this way. However, you should also know how to handle rational functions and, say, square root functions. These use slightly different algebraic maneuvers to enable you to get to a point where you can evaluate this limit. Okay, for our next example, we're going to try to calculate the derivative of f of x equal to 5 over x. While I'm erasing the board, you tell me what f of x plus h is, because after all, we're going to need f of x plus h. Okay, now, if you have thought this through, f of anything should be written as 5 over that something. f of 2 is 5 over 2. f of 3 is 5 over 3. So f of x plus h is 5 over x plus h. Okay? Bearing that in mind, let's calculate the derivative. F of x was given to us as 5 over x, and f of anything is 5 over that something, so f of x plus h is 5 over x plus h. We need f of x and f of x plus h in order to get started. This gives us the limit as h approaches 0. Now, f of x plus h is 5 over x plus h minus f of x, which is 5 over x over h. The limit as h approaches 0 of that. Once again, of course, you cannot just let h be 0 because you would have division by 0. The way we handle this is to use the so-called fundamental principle of fractions that says it's perfectly all right to multiply the top and the bottom of a fraction by the same non-zero quantity. You will get an equivalent fraction. Now, what I'm going to do here is to multiply the top and the bottom of this fraction by the product of these two denominators. In other words, to multiply by x times x plus h. This is how we often simplify complex fractions, which is what we have here, a fraction whose numerator or denominator contains fractions themselves. Okay? So we have one fraction minus another, this is what's going to happen here, over h. And I have said that one of the simplest ways of handling this is to multiply top and bottom by the product of the denominators. Now let's see what happens. We will have, once again, the distributive law holds, we have like a minus b times c. It's going to be a times c minus b times c. Let's see what happens. We have 5 over x plus h times x plus h minus 5 over x times x plus h. 5 over x plus h times the product of the denominators minus 5 over x times the product of the denominators. Now, in the denominator, we have the h times the x plus h. So let's see. Limit as h approaches 0. The denominator is h times x plus h. But the numerator is going to simplify. We're no longer going to have fractions in the numerator. Okay, this is really over 1. So what happens? We have 5 over x plus h times x plus h. Here, the x plus h's cancel, and we're left with 5x minus 5 over x times x plus h. The x's cancel, and we're left with 5 times x plus h. So at least we no longer have a complex fraction. Let's write that over here. We have the limit as h approaches 0, 5x minus 5 times x plus h all over h times x plus h. Now, let's simplify. In the numerator, we have 5x. Now, the minus 5 has to be distributed through the parentheses. We have minus 5x minus 5h over h times x plus h. The 5x's cancel, giving us the limit as h approaches 0 of minus 5h over h times x plus h. And this algebraic maneuver that we use to eliminate the complex fraction, multiplying top and bottom by the product of the denominators has put us into a desirable position where h is now a factor in the numerator. Once h is a factor in the numerator, it can cancel the h that's causing us all the trouble in the denominator. As h approaches 0, it's not equal. It's just getting close to 0. We can divide numerator and denominator by h, leaving us with the limit as h approaches 0 of minus 5 over x times x plus h. Now, as h approaches 0, this h is downstairs, but it's not a factor in the denominator. Okay, it's just part of a factor. If h goes to 0, what happens? We get minus 5 over x times x plus 0, or minus 5 over x times x, or minus 5 over x squared for our derivative. So we were able to work out if the function is of f of x is 5 over x, using the definition of the derivative, f prime of x is minus 5 over x squared. For our last example today, let us work with a square root function. F of x is the square root of x minus 1. Okay, figure out f of x plus h. Okay, f of x is the square root of x minus 1. F of anything would be the square root of that something minus 1. So f of x plus h would be the square root of x plus h minus 1. F of anything is the square root of that something minus 1. F of 5 would be the square root of 5 minus 1. F of x plus h, the square root of x plus h minus 1. F of x is the square root of x minus 1. F of anything, the square root of that something minus 1. F of x plus h, the square root of x plus h minus 1. So let's substitute now into our definition. The limit as h approaches 0. Now we need f of x plus h, which is the square root of x plus h minus 1, minus f of x, which is the square root of x minus 1 over h. Now, when we were handling polynomials, all we had to do was basically expand f of x plus h, subtract off f of x, and eventually h came out as a factor of the numerator and canceled the h downstairs. When we were working out a rational function before 5 over x, the algebraic maneuver that we used was to multiply top and bottom of the fraction by the product of the denominators. Okay? When you're handling a square root function in this form, we use the same idea we had before, that we are allowed to multiply top and bottom by the same quantity, same non-zero quantity. It's just that we use a slightly different idea here. If you think of this as a minus b, I want to multiply the top and the bottom by a plus b. So I'm going to write the square root of x plus h minus 1 plus the square root of x minus 1 over, of course, the same thing, because whatever you do to the numerator, you must do to the denominator as well. I'm going to think of this as a minus b, this square root minus this square root, a minus b, and I'm going to multiply top and bottom by a plus b. In other words, multiply by a plus b over a plus b. Multiply by the sum of the square roots over the sum of the square roots. Now, you might say, this is going to make life easier. It looks like a mess. Well, it's true the denominator looks like it's getting a little messy. The denominator becomes h times the sum of the square roots, x plus h minus 1 under the radical, and then the square root of x minus 1. So the denominator is obviously messier than we started with. The numerator, however, simplifies quite a bit, because what you have here is really a minus b times a plus b. And if you'll remember, a minus b times a plus b, when you multiply, okay, first you get a squared. The outer and the inner, plus ab and minus ab, cancel out. The last is minus b squared. Okay? A minus b times a plus b is a squared minus b squared. You very often learn this in algebra as a way of factoring the difference of two squares. The sum of the numbers times the difference of the numbers. Okay, here we're using it as a minus b times a plus b is a squared minus b squared. Well, if that's true, let's look over here. A minus b times a plus b should be a squared minus b squared. But when you square a square root, you're just going to get what's under the radical. So what you're going to get here is x plus h minus 1 minus, in parentheses, x minus 1. Let's look again. This is a minus b times a plus b. You should get a squared minus b squared. This squared, however, just gives you what's under the radical, minus this squared gives you what's under the radical. Okay? Limit as h approaches 0. The denominator is still a mess. The square root of x plus h minus 1, h times the square root of x plus h minus 1, plus the square root of x minus 1. Let's see what happens upstairs. We have x plus h minus 1. Now minus, it's like a minus 1 to be distributed through the second parentheses here, minus x plus 1. Okay? The x's cancel out, and the plus 1 and the minus 1 cancel out. So what we're left with here is the limit as h approaches 0. We have on top just an h over h times the sum of the square roots. Square root of x plus h minus 1 plus the square root of x minus 1. Now, once again, we have succeeded in getting h as a factor upstairs, and we can cancel the h's. When you cancel the h's, remember, you're really dividing numerator and denominator by h. If there's nothing remaining upstairs, is really a 1, not a 0 upstairs, it's a 1. Because when you divide by h divided by h is a 1. H divided by h is a 1. So you're left with a 1 upstairs over the square root of x plus h minus 1 plus the square root of x minus 1. And at this stage, we can find our limit by substitution. Because as h goes to 0, the entire denominator does not go to 0. We get 1 over the square root of x minus 1 plus the square root of x minus 1, which gives us 1 over. Now, if you have the square root of x minus 1 and the square root of x minus 1, you have 2 of those square roots. So 1 over 2 times the square root of x minus 1 as our derivative for this function. So if f of x is the square root of x minus 1, we were able to use the definition of the derivative to show that f prime of x is 1 over 2 times the square root of x minus 1. If it's a polynomial, basically you can go right into the definition of the derivative. You just expand, do what you're told to do here, and h will be a factor in the numerator and cancel out the h in the denominator. When you have a rational function, the algebraic maneuver is to multiply top and bottom, when you write it in this form, by the product of the denominators. And when you have a square root function like this, the maneuver is to multiply top and bottom by the sum of the square roots. Okay, and that brings us to the end of this videotape.